So, hi all. Welcome to my first episode on a series I'm going to try to do about programming in C. And I'm going to start at the very beginning today and not even probably get to C in this first video. And I'm going to talk about something that I think sometimes is underserved in classes. I am going to go back and talk about the concept of memory at a very fundamental level, because memory for a lower level language like C, memory management is very important. It's more important than in some other higher level languages where garbage collection and whatever means a lot of this stuff is done for you. But in C, you pretty much have to deal with memory yourself. So it's really important to understand the conceptual model that you're dealing with. So first of all, I mean, there's many types of memory, but when we're talking about coding in C, we're only, or any low-level language, we're really talking about one type of memory, and that's RAM, which is random access memory. And RAM has a couple of key properties that we care about. It's typically volatile, and what that means is that while the contents will stay what you set them to for the entire time a computer is turned on, when you turn power off, the contents are gone. And next time you turn the computer on, they could be anything. So the implication here is that we don't persist memory between sessions. Program runs, the memory contains garbage or nothing. It always contains something, but it's undefined. So typically when you start a program, you have to get data from somewhere else. And somewhere else might be a file on disk, or it might be from whatever somebody is typing at the keyboard, or it might be coming over the network, but it has to come from somewhere into memory before we can do anything with that data. Next concept, RAM is read-write. And this kind of makes sense, right? You have to be able to change it if the contents are undefined. You have to be able to set them to something that makes sense. And once you put it there, you have to be able to get it back in order to be able to do anything with it. And a lot of operations are read, update, write, where you will read something out of a memory location, change it in some way that's interesting, and then write it back to memory. And the third property is something that's actually in the name, and that's random access. And this talks about how we would use memory. So random access means that you can change or read any part of memory irrespective of anything else you've done. You don't have to do some things in a sequential order where you read memory from start to end. You can skip around as much as you like and read something that's totally unrelated to the last thing you read. And that third thing kind of gives us how we will access memory. So a lot of times we look for a real-world metaphor to help us understand something. So for memory, one thing I like to use as a metaphor is a post office box. So here you see a typical post office box. You've gone to the post office. I'm sure you've seen, this is a very close-in shot, but there are like walls of these. And you can rent one of these things and make it your mailing address. So you don't get your mail at the house, at your house or your apartment. You actually get it at the post office. And each box, as you can see, has a number on it. And the numbers are all sequential. So on the upper right, we probably have 23071, and then to the woman's hand to the right of that, we have 23072. And you can see also some numbers nearby that are cut off in this picture, but they're all basically sequential. And the box has contents, right? So somebody puts mail in or writes into the box, and then at some point the owner of the box comes, opens it with their key, and takes the mail out, which is equivalent to reading from the box. So memory is very, very like this. And in fact, we're just going to start and pretend that we're using the numbers on the post office box. So we saw a 23071 there, and there's going to be a 23072, and then there's going to be a 23073. And then we're just going to draw boxes on the page. So what can be in these boxes? Obviously, we can't put physical mail in RAM. So what goes in each of these boxes is called a byte. B-Y-T-E. And without getting too much into how this is represented in binary, a byte is just a number or in the range of 0 to 255 inclusive for a 256 combinations. So, okay, we have that, but what does it mean? There are multiple ways you can interpret this number, and we're going to talk about the most common ones. So, you've probably heard, or hopefully have heard the term von Neumann architecture. If you haven't, all it means is that the same memory that we use for data in a modern computer, in most modern computers, also holds the program. So if we have a number in here, it could mean, I'm just making numbers up here. I mean, this isn't for any particular computer. They're not real. But we could say the number 0 means to add. We could say the number 1 means to subtract. And we could say the number 2 means multiply, and you get the idea. So in machine language is just the interpretation of these numbers by the CPU. The CPU will look at a cell in memory, a byte in memory, and it'll say, oh, it's a 0. They want to add 2 numbers. It's a 1. They want to subtract 2 numbers. So obviously there have to be arguments here. So we could say that for add, it could be registers, it could be other memory locations. We're not going to talk about how it's encoded. The CPU will take from some location in memory, it'll take a number, it'll add it to another number, and it'll put it back into one of those locations. And that is the read, update, write that I was talking about earlier. So one use of memory is to store programs. So internally, the CPU will it has a register called the instruction pointer. And if we were talking about these boxes we already have, the instruction pointer would start at 23071. It would read the byte at 23071. It would execute that add instruction if there happened to be a 0 there, or subtract if there was a 1 or whatever. And then it would increment the instruction pointer and say, okay, now I'm going to do the instruction in 23072. And then I'm going to do the instruction at 23073. And it's just going to keep on doing that until the program ends. Now, you can imagine, what about loops or conditionals? If you already know a little bit of programming, you know about like if statements, you know about for loops. There are also instructions to test one number against each other, see if it's greater than or less than. There are instructions that change the instruction pointer. So the instruction set of a CPU is much more complicated than that. So it turns out that writing code using this stuff is possible, and it was done in the early days of computers. And machine language is typically used to refer to just using these straight opcodes. That's a real headache. So assembly language, which you may also have heard of, is the idea of using what the opcodes names are, and it's slightly better. It's slightly more readable than just 00012. Add, subtract, multiply is a little bit more readable. But still, it's really clunky, and nowadays nobody wants to do that unless there's a real reason, like there's something you can't express in a higher level language. Hence, languages like C, and then farther on, Java, Rust, any like more modern language you can think of. So, okay, memory can contain programs. We already alluded to the fact that memory can contain data. So let's talk about the different types of data that it might contain. So first of all, we're just going to talk about integers. So you might remember from math, an integer is any number with nothing past the decimal point. So 1 is an integer, 42 is an integer, pi 3.14 whatever is not an integer because it has a fractional part to the right of the decimal point. So here we've said that we can have 256 possible combinations. Okay, that's great. If we have 256 possible combinations, then we have the numbers from 0 to, as I said, from 0 to 255. So that's great for some things, but one thing you might notice is, well, all of those numbers are positive, and in the real world, we actually have negative numbers. So it turns out that you can tell the CPU to treat this number as a positive number, or you can tell it to treat it, which is, by the way, you'll see this term when we get to types in C. Unsigned means that the number is always going to be treated as positive. And if you want a number that might be negative, well, we're just going to say, okay, we're going to take this range and divide it in half. So instead of treating it as 0 to 255, we're going to treat it as from negative 128 to positive 127. And that's going to be known as a signed number. And in C, if you don't specify, you're always going to get a signed number because signed numbers are more common in general, and that's the default. So great, we have numbers, and I'm going to go over one other data type, and then we'll fix the problem. Maybe you see a problem here that numbers in that range are not very big, and in general, you can think of many things that are bigger than this that you would want to store. So we'll talk about how to deal with that in a second, but first we're going to talk about the third possible interpretation that we're going to talk about, and that is text. Because obviously, doing math on numbers is great, but at some point we're going to have to print this out in a form that a human can understand. Humans not going to want to go in there and poke around in memory and see what the answer was. I mean, 60 years ago when computers were in their infancy, that might have been okay, but now, like, people expect to be able to read the screen. So somehow we have to store text. And this is actually a way more complicated problem than you might think. So early on, computers could only deal with the Latin character set. And what I mean by that is the letters that and numbers that you think of as being associated with English. So the alphabet of A through Z, and also lowercase a through Z, the digits, and then some punctuation. These days that's not enough because we can't force everybody in the world to read English. It's a very Anglo-centric view of the world. It just doesn't work. And languages and the way their alphabets work are incredibly complicated, and there's this thing called Unicode that attempts to make it so you can have text in any language in the world. Some languages write their text from right to left as opposed to left to right, as we're used to in English. Some languages have characters that are superimposed on top of other characters to make new characters, and it's really complicated, so we're not going to talk about any of that yet. All we're going to talk about is Latin, and the Latin one is kind of the name of the character set now that we're going to talk about, and it's represented instead of by Unicode. The original encoding is something called ASCII. And ASCII only uses 127 of the possible 256 values that we can store. And the basic idea is that every number represents one character. So a couple of the common things you will find, if you can go online and search ASCII chart, and you'll see a nice matrix of characters and what they map to. And you'll notice that everything is nicely grouped into regions. There are reasons for that. But I'm just going to give you an idea of a few of the really common characters. So 32 is a space. And below 32 are all what we call control characters. Like the enter key is down there. The escape key is down there. Above that, we have some punctuation, and then we have numbers. So, and the numbers start at 48, and 48 is the digit 0. This is a very important distinction. 48 is a 0 printed on the screen. It is not a 0 to do math on the number 0. So it all depends on how you're interpreting. So if you have 48 in a byte, it could be the number 48, or it could be the digit 0 if you interpret that byte as ASCII. But you probably don't want to do math on 48 and expect it to be 0, because it's not. 65 is an uppercase A, and so on. And as you would expect, the letters and the numbers are sequential. So if we were to go one more, 49 here would be a 1, 66 here is a B, and then there's another range for the lowercase versions of the letters. And they have the very nice property that the way we would sort numbers alphabetically, so we would sort A before B, 65 is less than 66. So if we compare bytes that represent the characters, we get what we would think of kind of as like the what we call the lexicographic order, the order that we would sort these letters in if we were alphabetizing things. And again, that's also intentional. So that's all good. And now so I'm going to leave 4 until after I talk about another issue, which is what I promised you before. Well, this range of numbers is not very big. And also, when we're talking about text, we don't want to just print an A. We normally want to print a longer string. The canonical example is hello world. So how do we do that? And the answer is that we don't usually talk about just one byte of memory. We talk about a contiguous range of bytes. So we're going to go back and take our original bytes that we had here at 23071, 23072, and we are going to treat those as one quantity. And the CPU knows how to do this, right? I mean, I alluded to an add instruction. So the add instruction has variants. You can add 2 bytes together, but you can also treat multiple bytes in a row as part of the same number and operate on them as if they were just one thing. So what does this give us? So we said that there were 256 combinations that each byte could hold. Well, what are the combinations that 2 bytes can hold? Well, you just multiply these 2 things together and you get 65536. So you have about 65,000 possible combinations if you consider 2 bytes at a time. And early microcomputers, this was what you got, was about 64K. And if every byte is 8 bits, then 65536 is 16 bits, because we have 8 bits here and 8 bits here, and we just like add them together for the total number that we're using. So now, again, we could have numbers in the range of 0 to about 65,000, or we could have numbers in the range from about negative 32,000 to positive 32,000. Better, but still kind of low. And so we can take another step up, and we can start at 23071 and include up to 2301234 and have 4 bytes that we're talking about. And as you can imagine, since 256 times 256, now we have that multiplied together 4 times. So we have 256 to the 4th power. 256, by the way, since it's 8 bits, is 2 to the 8th. So this is 2 to the 8th to the 4th, or 2 to the 32nd, or 32 bits. If you're not used to seeing powers like this, I would read up on it, because taking powers of 2 in computer science is a thing we do all the time. So 2 to the 32, now we're in a range where we have about 4 billion possible combinations. Now we're getting somewhere. And in fact, on modern computers, you've probably heard that modern CPUs are 64-bit. So 64-bit in a modern computer means that we're using 64 bits to represent this address that we've been talking about. So addresses can be 4 billion times 4 billion, or like absolutely huge. So huge that we don't even have computers, even though they use 64-bit numbers for the address. Nobody has yet built a computer that can contain 4 billion times 4 billion bytes, because that's just an insane amount of memory. But it's there. As computers grow, they will grow into that address space. We thought when we had 4 billion, because this used to be 32-bit, that was a lot of memory, and now that's nothing. So, but even though we use 64 bits for the address, the default is 4 bytes for a number, just because you could use 8 bytes by default, but that just kind of doubles the amount of memory that your program takes. Your program is typically sitting there in memory alongside a lot of other programs, so even though there's a lot of memory these days, we still don't want to waste it. And 4 billion is enough for a lot of calculations. You can get an 8-byte number if you want. You just have to explicitly say that you want it. So great, that's how we get bigger numbers. And as you can imagine, we were talking about characters of text with ASCII. The idea there is very similar. So I'm going to write this 23071 again, but this time I'm going to draw the cells this way. And I'm going to just write the letters in here instead of the equivalent numbers, because that's easier to read. So this is how we do multiple characters of text. So this is called a string. So a string is just a bunch of ASCII characters and sequential bytes of memory. So in C, we would have the literal number 0 here at the end to tell us that we're at the end of a string. So hello is 5 bytes, but we actually store it in 6 bytes. So this would be in 23071 to 23076, and then the next available byte of memory after that would be 77. And when we get into C a little bit more, we'll talk a lot more about strings and how to operate on them. But the basic idea is, just like with using multiple bytes to form one number, we use multiple bytes to form one string, 1 byte per character. And the CPU actually does have some instructions that help you deal with multi-character strings like this. Okay, so one more thing. I promised you one more interpretation of memory from the 3 we already talked about. And this is a concept that people have a lot of trouble wrapping their heads around when they first start learning C. And that is the concept of a pointer. So I'm going to show you that it's not actually that bad. So I'm going to write over here our 23071, and we're going to assume we have this 4 bytes here, a typical integer, and it has the number 42 in it. So what if we had over here, say it's some other totally different address, say at address 2000. And because I said that these addresses are 64-bit, that's 8 bytes. So we're going to talk about the bytes from 2000 to 2007. So here we have a box that's 8 bytes long. And what we're going to put in that box is we're going to put the number 23071. So again, there are multiple ways to interpret that, but if we're interpreting that as a pointer, we're saying that what's in this box of 8 bytes is another memory address. So 2000 through 2007 is where this is stored, but what's in it is 23071, which is this 4 bytes over here, which have a 42 in it. If you see this drawn, a lot of times when we draw data structures out, we like to draw pictures of data structures because that makes them a lot easier to understand. But you will see this. You will see an arrow going from here to here. And what we're saying is, hey, this box here, this piece of memory here contains the address of this piece of memory over here. There are a ton of reasons why this is useful, and that will be in the next video. But for now, this is all a pointer is. All a pointer is taking a memory address and storing another piece of memory and treating it as the address of that other piece of memory. We talk about dereferencing in C. All dereferencing means is taking this 23071 in this box and following this arrow to get to this 42. That's it. All it means is going from this box to this box. And as I have said from many times on this lecture, the CPU has instructions to help us do this, and they are brought up into C, and C also has syntax to help us deal with this. So that's my introduction to memory, and I hope this was helpful. In the next lecture, we'll talk a little bit more about how this is useful. We'll start talking about what this looks like actually in C, and how the data structures and things in C that we use day to day actually are represented in memory, and hopefully that will help give you some clarity about why C does is laid out the way it is. So thanks for watching.